very much. Okay, so wait a second. Okay, so last time, so thank you for coming back. Last time, we were looking at these Hirzebruch-Young continuous fractions. So this is a recap of yesterday. Wall chains, you remember these three, how to construct these wall chains, which are particular continuous fractions. Remember that behind of a wall chain, you have the rational number n squared over na minus 1. And a wall chain is just the continuous fraction of this rational number. It always belongs to these three that we were discussing yesterday, that you have symmetry and also this mutation. And then we were talking about zero continuous fractions, mainly related to the dual of a general Hirzebruch-Young continuous fraction, and the dual was m over m minus q. So if you have this, then the dual is this, and then you have some other minimal continuous fraction. And then by subtracting here in some positions, we were looking at zero continuous fractions from here. So today I want to make that geometric. So I will start with the geometry of this Hirzebruch-Young, which are the cyclic quotient singularities. Then I will talk about the formations and obstructions. So the first part will be, if you want, like local geometry, and then global. We will do it on a projected surface. So then global. And basically, I will show you concrete examples. And then we will see what happens in this Collard-Sheffer-Barron Alexiv compactification of the moduli space of surfaces of general type. But again, like looking at particular invariants, not super general. Okay, so let me define the cyclic quotient continuous fractions. So this is definition 5. Okay, so just like in here, you remember that the GCD of M and Q are 1. So let Q and M be coprime integers. Then mu, let mu be e to the 2 pi I over m. So a root of unity, primitive. I take just that one. And then we have the automorphism of C2. So C2 to C2, given by x, y, going 2, and you put this mu, x, and then mu to the q, y. So this is an automorphism of C2. And then a cyclic quotient singularity is a singularity isomorphic to the germ at the image of 0 of C2 mod this action. So let me call this T. Okay, so that is the cyclic quotient singularity. You might define that in higher dimensions. Let us start with C. If you have C to C, you know, a cyclic action like x go to mu x, and then in the quotient you don't have a singularity, right? If you have a Riemann surface and a cyclic group acting, then you quotient by that group and you have, again, a Riemann surface. But when the dimension is 2 or more, then you get singularities. And this is dimension 2. The notation will be 1 over m, 1q. So you will see this notation everywhere in this talk. So it turns out maybe you have, I don't know if you have seen this before, so I'm talking to the students. So I will tell you how to construct this variety. So the variety C2 over T corresponds to the finitely generated C algebra of invariants. So C, X, Y, and you take the polynomials that are invariant under this action. So T. And now I construct an example. Example, if you take Q equals m minus 1 and m, then C, X, Y, set m, so under this action, this is Q, is generated by, okay, this is part of a homework that actually when you have a finite action, this is finitely generated. So if you put a G here, that is finite. So homework, this is finitely generated. And here I will show you generators for this particular case. If you see this action is on X and Y, so you need to look at the monomials only and then see how to kill this mu. So for example, X to the M is invariant because you put a power of mu and that is 1. So let us put those invariants. U equals X to the M, V equals Y to the M. And then here there is one more, and with that we generate everything, which is XY equals W. You see, because here you get mu, and here you have mu to the m minus 1, so you get m, and this is 1, and so it's invariant. And then 1 over m, 1m minus 1 can be thought as. So here you have the finitely generated algebra, and you have this with these 3 generators, but there is an obvious relation, and that is the relation here, which is this to the m is equal to uv. And you think about this in C3. Sorry?
What is CQS?
This is cyclic quotient singularity. So I never said that. Yeah, this is going to be, this is definition of a cyclic quotient singularity, sorry. Cyclic quotient singularity. Thank you. Okay, so that is the way we construct this quotient. So now I want to show you the relation with respect to the continuous fraction. By the way, this is this is part of this ADE or Duval or rational double point singularities, and this is of type A. I have to concentrate, m minus 1. Okay, so now, so for these cyclic quotient singularities, we have a trilogy that maybe, so this is the trilogy of, so you have 3 ways to think about these cyclic quotient singularities, but then maybe I will show you in the PDF. Okay, so this was the definition. This is the example, and now here you have the trilogy. So quotient is the definition that I just showed to you. So you have C2, you add, and you take the quotient. That's supposed to be a singularity. But then, so by looking at this, so you have the polynomial ring. You know, in orange, you have the algebras. Then you have the invariants. But here, independently of Q, you always have those invariants. So x to the m, y to the m, and this is always there, x to the q times m minus q times y. So if you plug in, you see m mu to the m minus q and then mu to the q, so they cancel. So you get an invariant. And here you have a relation again. So very similar to this situation. And so you have this hypersurface in C3 in between. And then with x to the m and y to the m, you go to C2 again. Oh, yeah, sorry. But this is exactly the orange part in this picture. So you have these inclusions, and then you can reverse to have the maps, the geometric maps. And over here, so you have the hypersurface corresponding to this, and then you have the projection on UV. And so this is a ramified map, which is cyclic, M to 1, which is ramified on the x's, on ux and on u equal to 0 and v equal to 0. But this is not normal in general. You have that this number is not 1 in general, and so you need to take normalization, and that would be the cyclic quotient singularity. And there you have the quotient. So this is the algebra, and those are the maps. So quotient, covering. But now we have this minimal resolution, where you replace that point by this chain of P1s, as you see here. And so now this surface in here is going to be smooth. And then these are P1s, and the self-intersection of the P1s are minus EI, and the EIs are the ones that you get from the continuous fraction. And in this red part, you see the toric picture, where here you have the algebra using this M. Then you have the dual that give you the geometry. So at the beginning, you have only this ray and that ray. But now you need to add these other rays to make this toric variety smooth. And that is the resolution. And that is how you get there. So if you do the computations, then you will get, in the computations, you will get the recursion that will give you the continuous fraction. So that is the trilogy. So you have the chain that contracts, or you have the quotient, or you have the covering. Hmm? Oh, yeah, sorry. Yeah, it's reversed. Yeah. Thank you. It's like this. Thank you. Yeah. Okay. So that is how this Hirschenbruch-Jung continuous fraction appears. Okay, so some practical facts that I will use. So one of them is that if you have, so say that we are in the situation of a smooth surface, and inside of that smooth surface, I have this chain of rational curves that have these self-intersections given by an M over Q. Then you can contract that chain, and that is the Artin contraction criteria. So given Hirschenbruch-Jung chain, say sum of EIs. This is going to be my notation for the P1s the whole time, the exceptional P1s. This is R inside of X, non-singular. can always be contracted into a 1 over m 1q. And if you start with something projective, if x projective, then the contraction, so say that this is the contraction, x going to x bar, the contraction. Contraction means birational map that contracts this chain. Then x bar is projected. This is arting. So we will use all the time this criterion. So the thing with these Q-Gorenstein smoothing and the degenerations I will talk about is that they are very abstract. The only thing that is concrete somehow is this x. And then we have the smoothing like an abstract thing. And so to have this x, we will start with something smooth and some chain of curves, and then we will contract to have the x bar, which is going to be this degeneration. Okay, now another thing that is useful to mention is that we have an intersection theory too. So on a normal projective surface, so like this one, we have intersection theory. So this was defined by Mumford. And I will explain how this works. So the key to define these intersections is that the EIs, so for each singularity, you have the intersection of the exceptionals, and this is negative definite. And so when if you have a singular surface, say with singularities here, and you have some curves, and you want to intersect, then the idea is to pull back. So you have the minimal resolution here. This is my x bar. This is the minimal resolution. You will pull back. So you want to know how to define, so this is C and C prime. You want to know how to define C dot C prime. And for that, so you will have the proper transforms. Let me put a bar. But then, sorry, this is plus. You have the proper transforms. Oh, this is too small. I will move it to the other board. So C, I want to know C dot C prime. Then this is going to be equal, this is birational, to the pullbacks of C dot pullback C prime. But now I take the proper transforms. No, bar C prime. But then there is something to put here in relation to the exceptional curves. So there are some numbers here. I don't know how to call them. EI, FI, EI. But then, you know, I can forget. I don't need to have in both sides because this is pullback. So EI dot this pullback is 0. So maybe let me consider this like that. But now the question is, so and then this intersection is going to be this intersection, but how to find these EIs? So the EIs are uniquely defined via, you know, intersections with the because this is negative definite, so if you have, this is very messy explanation, but it's the way it works. You have something like this, and now you intersect with the EJs for every J, and you have a matrix. You want to find these numbers, but this is invertible, and say that we know how the EJs intersect the C bar, and this is 0. So you have a system, and then you find the numbers. And when you find the numbers, you intersect, and you have these intersection numbers. And they are rational. So intersections are now rational numbers. Okay, so one of the important numbers that appear here are the discrepancies. So when you look at the pullback of the canonical class, so here you will have a canonical class for the singular variety, which is going to be denoted a canonical divisor, denoted by kx bar, and here you have a canonical divisor, kx, and of course there is some relation under this pullback, and the relation is like this. So you pull back the canonical class downstairs. This is going to be numerically the canonical class upstairs. But now here you need to put, again, like in here, these numbers, which are the discrepancies between these two canonical divisors. And these are the discrepancies that appear with the EIs. Where in here I'm thinking about several singularities. So this is maybe a double sum on EIs for the different singularities. And how you compute these DIs? Well, it's the same. You just intersect with the EJs. You know, this is pullback, so here you have 0. And then these are, so I'm thinking about only the cyclic quotient singularities. By the adjunction, you have EJ squared plus EJ dot K equal -2. This is adjunction. So you know this number is going to be -2 plus EJ. So you have again a system, and then you resolve for the DIs, and those are the discrepancies.
So all this has nothing to do with projectiveness, right?
No, nothing to do. This is local, yeah. Okay. So now, among those discrepancies, we care about this Wahl singularity. So 3, how to compute discrepancies for Wahl singularities. By the way, Wahl singularity is the singularity corresponding to a Wahl chain. So the ones, so Wahl singularity, parentheses, 1 over n squared, 1 and a minus 1. G, C, D, and a equals to 1. So how to do that? I was telling you about Fibonacci last time. I will show you an example. I don't want to write the recipe because it could be, you know, it's in the note. Maybe let me give you an example, and I will do, maybe I will show you the example, and I will do exactly the same as I did yesterday. So that is the example. This is a Wahl chain. I'm trying to give you a practical way to just compute things. You know this is Wahl chain because here you have 3 2s. Oh, I forgot 1 2. I'm sorry about that. Let me see. Is there any other mistake? No. There is one more 2. So maybe let me write it down. That is not Wahl chain. So let me put it example. So 6, 2, 2, 3, 2, 2, then 7, then 5, then 2, 2, 2. Because if you have this, then you subtract these 3 2 to this 6, then this is 3, and I have 3 and 5, so there is no 2 to continue the process. I need one more. So this is Wahl. I subtract 4, I get 2, then 1, 2, 3, I subtract 2, 5, so I get 2 here. Then I subtract here, I get 2, then 1, 2, 3, I get 2 here, and this is, sorry about that. I don't know why and this is 5. So 4, 2, 2, 2, 2, 2, 2. No, sorry, this is 7, it's okay. 4, 2, 3, 2, 2, yes, it's okay, okay. There was only 1, 2 missing. And so now, I compute these numbers in red, which is, you remember that you go to the center. This is where the process started, the algorithm. And so to that center, you put a 1, and then you add 1 plus 1, and jump to the next, which is this 2. So this 2, 3, 4. But now you need to go into the other direction. So 4 plus 1 is 5. But now we change direction again. This is 9, 14, 19. And maybe now I need the help of this. So it's 24. And then 43. And then 62. And then the next one is not the n. It's going to be 81. And now n is 81 plus 19, which is 100. And then a, so it depends on how you want to think about this continuous fraction. In this way, it would be this a. So that would be 19. So how to compute from these numbers in red the discrepancies? Then it's very easy for each of these numbers. You have a fraction, which is going to be the discrepancy that, by the way, in the case of cyclic quotient singularities, these numbers are going to be between -1 and 0. These are the di's. So you can prove that always is that the case. And then for the discrepancies here, what you do is you put the n. N is going to be the denominator, so it's going to be like 100. But now you put a minus, and on the top, you have 100 minus 19. So this number, 81. And then you have the collection doing the same thing. So always denominator is going to be n, and numerator is n minus this red number, and then with a minus. For example, in this case, you always have a 1. So here is always minus n minus 1 over n. And this is the most negative discrepancy in a Wahl chain. Another thing is that when you have these 2, you know this discrepancy is going to be not so, is always, when you have a 2, is always over 1 minus 1 over 2. And that has consequences that we will use later. So in this case, it's minus 19. This is 100. So the only point that I wanted to do is that there is a nice algorithm using this Fibonacci type of thing to compute the discrepancies. You don't need to go to the linear system. You show me a Wahl chain, and I compute immediately discrepancies. But using that, you can prove the following theorem, which is written there. So well, it turns out that you can show that the index of these Wahl singularities, which is 1 over n squared and so on, is n, not n squared. Index means the number that you need to multiply the canonical divisor to make it Cartier. The canonical divisor, when you have a singularity, is only Q Cartier. So the smallest number that you need to multiply this canonical divisor to make it Cartier is the index. And for the case of Wahl singularities, is n. And using this algorithm, you can prove that this n is bounded by the R Fibonacci number, where Fibonacci numbers, we think about them in this way. And exactly, you have equality. So equality, you achieve equality in that theorem. So n is exactly fr, if and only if you have the situation 5, and then only 3's on both sides. And of course, you need at the end a 2. This kind of situation.
Can I ask, is this, I mean, this algorithm, is it special for the Wahl singularities?
Yes, it's special. No, it's special for Wahl singularities.
For any chain, is there some algorithm that
I don't know. No, I would have to do this kind of thing. Of course, okay. No, it's not true. I can show you how to create two sequences of numbers and then compute the discrepancy with those sequences. So I need to, no, there is a way. There is a way to do it, yes. But here it's very simple. It's very direct. And the way to do it is also in the note, where we have these alpha i's and beta i's, just in case you saw it. Okay, so that's it with respect to the singularities and a bit of intersection theory and how you compute intersections. Still, I'm not showing you an example, but it's coming up. But now I want to introduce, because I want to do both at the same time, deformations. So a cyclic quotient singularity, 1 over m, 1q, has, in general, several ways to smooth. And this is particular of dimension 2. If you go to dimension bigger or equal than 3, they are rigid. So it's completely different. It's not only that you don't have several ways, but you don't have any way. But for dimension 2, you have a lot of ways, and my goal now is to explain how. But now some notation in relation to deformations. Okay, so this is going to be the notation. This D is going to be the germ of a non-singular curve. All deformations for me are going to be over D and no other base. Then a deformation of X, a given X over D, is going to be an irreducible reduced threefold, which is fiber. So this is the threefold denotation, fancy X, which is fiber over D, such that X is a fiber. Okay? And so you have this situation. You have the threefold over D, you have a fibration, and X is going to be over a distinguished point that I will denote by 0. You think about D as a disk, as I say there, but I don't care about the radius of the disk. And then for any other t, you have the xt. So this is going to be the picture. A picture like this indicates a deformation. Or sometimes I will use that notation that xt degenerates to x, okay, notation. A smoothing is a deformation where this xt is non-singular. So there are no singularities. And so a smoothing of x is like that, or you might say a degeneration of xt into x. And a Q-Gorenstein smoothing is a smoothing with the canonical class of the threefold Q Cartier. Okay? So those are notation definitions for what I'm going to do. Okay, so now I will study a little bit the deformation of a cyclic quotient singularity, and for that I need to introduce P resolutions. So I will define P resolutions, but for that I need to define first T singularities. And this is a definition due to Collard-Sheffer-Barron. Definition. So there is a paper in this whole story that is very important. This is Collard-Sheffer-Barron. This is 1988, and this is the paper where they define a compactification. They propose a compactification for the moduli space of surfaces of general type. But in the way to do that, they use Mori theory. They study, for example, the deformation space of this kind of singularity, or quotient singularities in general. It's also included in that paper. And for that, they define these T singularities. So a T singularity is a quotient singularity singularity. Quotient singularity means the same as before, but with any finite group. And there is a classification of them. So a quotient singularity is more general than cyclic quotient singularities. A quotient singularity that admits a Q-Gorenstein smoothing. So a situation like that, where this threefold has canonical class Q Cartier. Okay? And why? Because they naturally appear in this, to define this compactification. So what they do, they have a degeneration. There is a way to resolve that degeneration. Then you have some threefold that is smooth, and then you run MMP. But when you run MMP, all the time the canonical class is Q Cartier. So you end with something with canonical class Q Cartier. And so naturally, if you end with a quotient singularity, the deformation is Q Gorenstein. So they naturally appear in that sense. And then theorem, they prove immediately, theorem in the same paper, that a T singularity is either Duval or a cyclic quotient singularity of this type, 1 over d n squared dna minus 1, where the GCD of n and a is 1. So a little bit more general than Wahl singularities. Wahl singularities are these things with d equals to 1. Here, any d. So this is in the paper, KSB 88. Now, there may be, when you have a degeneration that has only Duval singularities, then you can resolve that deformation simultaneously. So instead of considering this singular degeneration, you consider a smooth deformation. So Duval singularities, in that sense, they work like smooth points, but not these ones. But then maybe I should have considered these singularities for any d, not just Wahl singularities. But yesterday in the TA session, I told you that you have the following observation, M resolution. So it turns out that when you have a T singularity, a general T singularity, you can always consider an M resolution, and this looks like this. So say that here you have the Hirschenbruch-Jung minimal continuous fraction corresponding to this T singularity. So by this, I mean you have the continuous fraction. And then you can partially resolve in this way. And you put a 1, and then you put the same. You put a 1 and continue, then you put a 1 here, and this Wahl singularity corresponding to the NA. I will give you an example so that you can see it in geometric terms. In the singular surface, you will have a chain of D P1s, and you have these Wahl singularities on the nodes. So you have the rational curves with these singularities on the nodes and also at the beginning here at the end. And these, so when you resolve, minimally resolve, you will get the resolution of this singularity, the same, but in between you have this -1 curve. and then -1 here, and then the other and the other. But you can contract that contraction to this singularity, to 1 over d n squared. And this is numerical. You can do it numerically. Let me show you one example at least. So for example, or maybe I can show you here. So this is what I just wrote. And this, yes?
When you say dp ones, do you mean the ones or the Wahl singularities?
So let us look at this example. So there, this chain corresponds to d equals to 2, n equals to 9, and a equals to 2. So this is a t chain, and now, okay, maybe.
So maybe d minus 1 would be 1.
Oh, d minus 1, that is correct, yes, not d minus 1. Because when d is 1, then we have only the Wahl singularity. Yes, d minus 1. And so here we have d equals to 2, so we will have only 1, 1, like in here. And, well, this t singularity looks like this, 5, 3, 4, 2, 2, 2. Okay, for t singularities, you have the same algorithm as for Wahl singularities. So let us see how this works. You eliminate these 2's, so to the 5, then you have a 2 here, and then you cancel this 2 with this 4, and you have a 3. So this starts with 3, 3. So we start with 4 when you want Wahl chains. This is d equals to 1. You start with 3, 3 when you have d equals to 2, and now you have a t chain. And in general, you start with a 3 and only 2's, and then 3 when d for any d. And the number of 2's in between is d minus 2. So in this case, this is the initial t chain for d equals to 2, and then you have that. And now how to do this partial resolution numerically? You have this center, and now over this comma, you need to blow up so that you will obtain eventually this Wahl chain. And you will get it on the left, and you will get it on the right. And what is the Wahl chain? It's exactly 5, 5, 2, 2, 2. And then it's repeated. So what happens? So for the Wahl singularities, you have this simultaneous resolution for the degeneration. For T singularities, you have this resolution, partial resolution, and consider the corresponding degeneration when you are considered here a Q-Gorenstein degeneration. So here you will have a Q-Gorenstein degeneration, but with only Wahl singularities. So at the end, you don't really need Duval and T singularities. The only thing that you need are Wahl singularities. And that is the point. Now, how to then study any degeneration, any deformation of these type of singularities? And for that, the tools are going to be P resolutions. It's going to be P resolutions, so let me define that. So this is definition. I mean, there are many things before I do an example, because we really need this language to express something. So sorry about that, too much maybe. A P resolution of a given cyclic quotient singularity is a partial resolution. So I will denote it by this, W going to my 1 over M 1Q. This is F. So this is my singularity. This is a singular surface in general, such that W has only T singularities. And here you include then Duval and these other ones. And canonical class of W is ample related to F. Relative to F. That means when you intersect, so here you have a canonical class. There are exceptional curves. When you intersect exceptional curves with the canonical class, you get positive numbers. Remember that they might be rational, but positive, and not zero, positive. And maybe this positive is the reason of P resolution.
I was going to ask you, there is any logic in T, M, P?
Yeah, T maybe for terminal. These are the deformations with terminal singularities. P, I guess this is P positive. And then we will have an N, which is negative, N resolution, but coming up. M minimal. So P resolution is like the canonical resolution, where you have really this. Then M resolution is for minimal.
One should teach these people how to use macros in Latin, right?
Well, yeah, there are always complaints about these names. Okay, so the theorem then. So maybe at this point you want to have a picture. So how do they look like, these P resolutions, for a given cyclic quotient singularity? So the theorem that they prove, Kolar-Sheffer-Barron also, a P resolution looks like this. So similar to this, you have a chain of P1s, gamma 1, gamma 2, so on, gamma L. And here you have singularities when they cross. You have singularities. And also maybe at some point at the ending curves. And this is a partial resolution over my Gaussian singularity, where the singularities are T singularities, the gamma i's are P1s, and when you see something like this with a gamma I plus 1, this is a toric boundary for the T singularity. And the T singularities are only of type A, or 1 over d n squared 1 dna minus 1. Okay, so these are toric singularities. You have a toric boundary. When you look at the singularity, these are representing these toric boundaries. If you want, when you minimally resolve these singularities on this chain, you have a whole chain, a big chain, like representing what we were seeing yesterday, like a chain with ones in between that you contract everything to the cyclic quotient singularity, or to the Hirschenbruch-Young continuous fraction of the cyclic quotient singularity. Okay, so that is the picture. I will show you now an example. Well, there are finitely many also. There are finitely many P resolutions for a given Okay, let me show you an example, which is in the paper. So if you take m equals 19 and q equals 7, then m over q is 3, 4, 2. So if you do so this is 3 minus 1 over 4 minus 1 over 2. You can compute here. You have 8 minus 1 is 7, so you have the 2 here, and then 7, 3. You have 7, 3, you have 21, minus 2, you have 19. It's okay. And then I will show you how to, well, so here, so for 1 over 19, 1, 7, we have 3 P resolutions. So in principle, what you do is to blow up at nodes and compute discrepancies and find what they call a maximal resolution for this singularity. And then this maximal resolution will dominate all the P resolutions. That is the way that Collar, Sheffer-Barron did it. I don't want to even define that, because we will do it with zero continuous fractions. So what you need to do here, when I say 3 P resolutions, you need to go to the dual. So 19 over, and then 19 minus 7 is 12. And now we need to compute that, but maybe I remind you how to compute that. You do the dot diagrams. So here I have 3, you put 2 dots. Now below this, you put 3 dots because you have 4. And then below that one, you put 1 dot. So when you add to the right, you have 3, 4, 2, and you recover this fraction. But now you add 1 down, and you have 2, 3, 2, 3. And this is the fraction corresponding to 19 over 12. So 3, 2, 3, 2, 3. And now with this fraction, you want to find positions where to subtract and get a zero continuous fraction. Different positions, different DIs. And it turns out that there are only 3 possibilities. That maybe, I have them here. So you have these 3 possibilities. Let me write them down. So here is 1 over 19, 1, 7. And over this, you have these partial resolutions. So, for example, this is practically a minimal resolution. You know, minus 3, minus 4. And we would like to put minus 2 here, but minus 2 dot, so the canonical class dot this minus 2 curve is 0. So you need to contract it. And then you have this A1 singularity. So this is one of them. The other one contracts in the minimal resolution, the minus 4. That is the first Wahl singularity, the 1 over 4, 1, 1. And so you have a situation like this. Now, yeah, so this is 4. And now here you have the 2. When I write minus 3 here or minus 2, that is not the self-intersection of this curve in the singular surface. It's not. I'm trying to remember what is the self-intersection in the minimal resolution, okay? In case you see it more times, that is the convention for me. And then for the last one, so you have 3, minus 4, minus 2. If you do just one blow up here, you will get minus 4, minus 1, minus 5, minus 2. And you recognize this is minus 4, so it's a Wahl chain, and this phi 2 is also a Wahl chain. You compute discrepancies to check if this curve is positive, and it is, and then this is a P resolution, and that is the last one. So this is 4, then again my notation, and this is phi 2. You want me to compute the canonical class dot this curve to check that it's positive? Yes? No? I'll do it. I'll do it here. Let me erase this. So how you compute self-intersection of this curve with canonical class, like we did intersection at the beginning. You need to pull back canonical class, so say this is gamma, and this is W. This is inside of a W. Then I want to compute gamma dot kW. So then I pull back. But when I pull back both, then there are exceptional divisors here and there. So I will forget about the ones for gamma. I don't care about them, but I will keep the ones for K, which I know, because those are the discrepancies, where the discrepancies appear. And then this is gamma prime upstairs. So dot K of X. And then you remember that when you have the discrepancies, you remember this, Kx, numerically pull back of Kw plus the sum of the discrepancies, di's, ei's. So in here, I have the pullback, so it's going to be this minus that. Remember that the discrepancies are negative, so now they are going to be positive in here. So you have plus, and then the discrepancy for 4 is 1 over 2. Let me call the exceptional E1. And then for the other, you know I have phi 2. So I put here a 1, then a 2, 3, and so the discrepancy for this one is minus 2 over 3, and for that one is minus 1 over 3. So this is 2 over 3, E2. Let me say that this is E2 and this is E3 plus 1 over 3, E3. So what matters here is the curve that touches, so that intersects this gamma prime. So this one is intersecting gamma prime and this one. And gamma prime is a minus 1 curve. So the intersection of this with canonical class is minus 1. Then it's transversal to E1, so you get plus 1 over 2. And then it's transversal to E2, so you get plus at 1 point, so you get 2 over 3. And that should be positive. So 6, 7, 1 over 6, positive. So this is a P resolution.
Can I ask something? So in practice, right, in the cyclic case, the P resolutions are all like toric over, you know, they're toric just like the quotient singularity. Is that obvious from the definition of the P resolution?
No, I think that, so from the definition, you go and try to see this maximal resolution, and this maximal resolution has to be a chain. So the question is about a chain. You don't want to have like other direction. So you can prove that it is a chain, and then this is over any P resolution. So you will have always chains, and then this is like toric. Yeah, there is something that has to be proved.
So when you say there's only that many P resolutions, are you assuming that these P resolutions are minimal as P resolutions, or are you just claiming that if you say pull up any random extra points that you don't need,
These are all the P resolutions. So you can compute using the dual fraction that all the ways, so if you try to make this 3, this 2, 3, is that the question? You want to make it 0, then there are only 3 possibilities, and that is in bijection with the P resolutions.
if I have then one of the 3 P resolutions and I then pull up maybe one more point that I didn't need, then
That is, it's not going to work. That is the point. Yeah. If you keep blowing up and try to make another one, something negative or 0 will appear. Yes, it's not going to work.
And then if I start off with a singularity that isn't a cyclic quotient, do I still only have finally many of these P resolutions?
Yeah, for some, okay. So when you have a quotient singularity, you can also prove that there are finitely many, and they are in correspondence with the components of the deformation space. I'm going there. But in general, I think that Collar has this conjecture that when you have a rational singularity, there are also P resolutions that are governing, that are labeling the components of the deformation space, and you have finitely many deformation space. But I think that the question there is what is exactly a P resolution? It's not clear. Yeah, for this definition, I'm thinking about W like a normal surface with this type of singularity, so it doesn't work like this. You need something more general.
But the expectation is that there's still only finally many.
There are finally many, yes.
You know what it is.
Yeah, so the expectation is that there are finally many, and we, in general, for rational singularities, we don't know what they are. But there are some papers.
Not everybody believes it. Not all hacking
Does not believe? Okay.
I have a question. Why do not the singularities of type D and E appear in a clear resolution? Because they are also.
Why the D and E do not appear? Yeah, it's because of this chain that you can prove that for cyclic quotient singularities, you will have a chain that is over all the periods. Yes. So these will not appear, yes. But for quotient singularities, they appear. Yeah, in general, yeah, for quotient singularities. So now I will show you some, what time is it? Ooh. Okay, so this is the thing. When, so there is a deformation space for the cyclic quotient singularity, and you have several components of this deformation space. And it turns out that using this Mori theory, they can prove that these components are in one-to-one correspondence, and it is in the paper of Kolar-Sheffer-Barron with these P resolutions. And this is geometric, as I said there in blue. So what is the geometry? You have the cyclic quotient singularity, you take the P resolution, and now you consider Q-Gorenstein smoothings of the P resolution, and those Q-Gorenstein smoothing blow down to smoothings of the cyclic quotient singularity. So it's very geometric, and in that way you understand all the smoothings of a cyclic quotient singularity using the P resolutions. That is in one-to-one correspondence, but now Christoffersen and Stevens prove this combinatorial way to think about these P resolutions, which are related to these zero continuous fractions. So you have zero continuous fractions where the length is the length of the continuous fraction of the dual. Remember I told you that the dual of the continuous fraction of the cyclic quotient singularity is the one in charge of the deformations of the cyclic quotient singularity. So you look at the dual, you see it there, and now you're trying to find zero continuous fractions with this case, so that the k's are between 1 and the bi's. And in that way, when you find one of them, then I can construct one of these. And there is a recipe for that. And the recipe is in papers, but it's also in the notes, in case you want to check that. I don't want to show you that. And then Venki Christoffersen proved that they are in one-to-one correspondence with these M resolutions. And M resolution for us will mean, you know, when you have this P resolution, if you see a T singularity, like 1 over D n squared, then you replace that by this chain of Wahl singularities with these -1 curves connecting, the thing that I showed you. And when you see an A singularity, you resolve it. And that is in one-to-one correspondence with these P resolutions. And then recently, because of semi-orthogonal decompositions that appear in the degenerations with these singularities, we define these N resolutions, N for negative. And so you have a similar situation as in P resolutions, but with only Wahl singularities. And by the way, with M resolutions, since you resolve the A singularities and the T singularities with D bigger than 1, then you have only Wahl singularities in here, only Wahl. For example, the minimal resolution is a M resolution. For N resolutions, you have also Wahl singularities, a chain, but now the curves that appear intersect the canonical class, the canonical divisor, non-positively. So 0 or negative. But this is not only the condition, there is something else. Because if you put only that, then there are infinitely many. That will appear when I talk about birational geometry. This is like you know, M resolution is going to be like the positive side of a flip, which is unique. N resolution has to do with the negative side, which is not unique. There are actually infinitely many, so you need to fix something else. But when you fix it, you can prove that this is in one-to-one correspondence with N resolutions.
Okay, so can I, just the very first part of this correspondence.
Yes?
Is it possible to say briefly what is the idea with this?
Yeah, so the idea is that you have a degeneration, a smoothing of the cyclic quotient singularity, and now you can resolve, like, to do this semi-stable reduction. So you have a smooth space upstairs, and now you run MMP over D, and then you go to the answer that gives you, and the answer is exactly a P resolution. So you have so you have over the singularity. You will see that over the singularity you will have this P resolution, which is now. So you go to the canonical model of this. So you go to the minimal, then to the canonical model of this smoothing, and you will see the P resolution appearing from there. And they prove that, yes, that there is.
Like in this case, where everything is toric. So on the right-hand side, I have some like toric. I've added some rays or whatever to my toric diagram. Is there a way of, seeing these smoothings in some toric picture? It's kind of
yes. Yeah, like a concrete model for the smoothings, the Q-Gorenstein smoothings of the.
From like the toric
Yeah.
bone or whatever.
Yes, we can do that. Yes.
Kind of like hacking stuff.
Yes, exactly. Yes, yeah, we can do that. Okay, so now global. So I have until 12:30. Okay, so now global. So now you have a W that is a normal projective surface where we have these Wahl singularities. And the question is, are there smoothings of W over D, or more specifically, Q-Gorenstein smoothings? So how to construct Q-Gorenstein smoothings of these surfaces? And so for this, I need to explain a little bit on obstructions and things like that. So the thing is that when you have a W like this, there is a deformation space for this W, like a general theorem. There is a versal deformation space that I denote by def X, which is a complex analytic space, so like where you can see all the deformations of this X. So all ways to deform this X. And for example, but this is again local, if you look at the singularity, the AN singularity, then this def X for AN would be the C to the N, and then this is the universal family over that base. So on X, you have the one forms and the dual. So if X is non-singular, then this chief of differentials is locally free, and then the dual 2, and this is locally free of rank 2. But in our case, it's just what it is, chief of differentials and the dual. And then the tangent space of this deformation space, let us denote that by T1X. The T0X are going to be the infinitesimal automorphism group of this X, and the obstructions to the form. So what we mean by obstructions, when you have here in this tangent space some direction, you know that is not really a deformation, it's just X and some direction. We want to have from there an actual deformation, but then there are obstructions, and where those obstructions live in this T2X. And so there is this map, and when you have these classes, you want to see if this goes to 0 or not. When they go to 0, then you can construct an actual deformation. So you have a similar picture. Sorry, but it seems like I don't have maybe enough time to do the example, but so then I have to go a little bit quicker now. So we care about Q-Gorenstein deformation, and there is a similar picture. There is a T0 QG, Q-Gorenstein, T1, which is the tangent space, and T2. Okay, obstruction, tangent, and automorphism. One can prove that this T0 is going to be actually the sections of the TW. And then that we have this exact sequence, where here you have the T2, here you have the H2 and H1 of the TW. This is the tangent space, and this is a sum of C's over the Wahl singularities that you have in W. So here you have the tangent space. This is representing deformations that are going to be constant on singularities, so equisingular deformations. And over there, you have the smoothings of the Wahl singularities. So it's like split into smoothings and equisingular deformations. It turns out that when you have a T singularity, you remember 1 over D n squared. This D is the dimension of the Q-Gorenstein component of the corresponding deformation space of that T singularity. So if you have a T singularity, there might be many components of the deformation space, but there is only one where the Q-Gorenstein smoothings happen. And that one has dimension D. So for Wahl singularities, D is 1, so the dimension is 1, and you think about that as a C. And that is why we have a sum of C's. And so for Wahl singularities, you only smooth, and there is only one way to do it. Okay. And then, so by theorem of Itaka, if you have the canonical, the KW is big, then the automorphism of W is finite, and so this H0 TW is 0. And then using Riemann-Roch, you can compute dimensions, at least to have some dimensions to compute, and you have that the tangent space is going to be, this is Riemann-Roch, 10 times the Euler characteristic of W, minus 2 K squared W, and then plus the obstruction space. And so you have this formula here. Now, the thing is, so to tell you how this works, the thing is this theorem that if you have that this H2 is 0, then this T2, the obstructions, is going to be 0 because I showed you this picture here, right? If this is 0, this has to be 0, and so there are no obstructions. And when that happens, you can consider the formations of your W. And that is the way we construct the formations for a W. So I told you that the only concrete thing that we can construct is the singular W. And then if you're lucky enough and compute that this is 0, you have no obstructions, and you can consider the formations of that W. And actually, you can choose, because if this is 0, then you can glue the local deformations you want on the singularities to have a global deformation of W. And we choose the ones that are Q-Gorenstein. And so we have a Q-Gorenstein smoothing of the surface. So for example, when PG, which is the H2 of OW, is 0, and Q, which is the H1 of OW, is 0, then this H2TW can be 0 only in this interval. And why is that? It's because of this formula. You know, this number here is positive, and the K squared, so say that I want a K squared positive. K squared in these deformations that are Q-Gorenstein is constant. So if you want to have, for example, something of general type, then you need K squared positive. So it would be also positive, this one. And so the only thing that is negative is in here. But then you realize that to have this 0, you are forced to only consider K squares between 1 and 4. So for 5, you have problems. For 5, this is 0. At least you have one Wahl singularity, so this is not 0. So you know when K squared increases, then to have obstructions is more likely. Okay, so let me show you finally some examples that are very concrete. So I was answering this question of the geometry of these Wahl chains yesterday in the TA session. And this is the geometry I explained before. So when you have an elliptic surface, you have this type of degeneration of this genus 1 curve. This is called I1 fiber. And so the self-intersection is written there is 0. And then when you do a blow up on the node, you have that the self-intersection of the proper transform is 4, because this is a double point. You have the -1 curve, and this -4 is going to be the first Wahl chain, right? And then you take a node, the intersection between the -1 and the -4, you can choose, but here it doesn't matter because you will have 2, 5 in one way or the other. And after that, you have a new -1 curve, you have 2 nodes, and you do the blow up, and then you see the algorithm of Wahl chains appears. So this is the geometry of the algorithm, if you want. So let us construct something using a pencil of cubics in P2. So you know we have C1 and C2 cubic curves in the plane, and you consider the pencil, so you have 9 points of intersections, and we blow them up to have an elliptic fibration. So here you have the elliptic fibration, and say that in this elliptic fibration we have 2 I1 fibers, like this. And you know, we are blowing up a pencil of cubics, so there are sections. And here I consider one section. Okay, I have this. And now I blow up this node and the other one, and so I have -4, -4. And from here, by arting, you can contract these 2 -4 to have these 2 singularities, and you have a W1, which is a normal projective surface with 2 Wahl singularities. If you keep going, just one more blow up, you have I2 and 4. You can also contract, and you have this W2 that has these 2 singularities. Now, I want to show you that you can actually smooth those singularities. So how? By proving that the obstruction here and here is 0. So let us see how this obstruction works. So in general, so this is my W with singularities. You look at the minimal resolution, and you can compare this way. So this is a theorem that the H2 that I would like to make it 0 is exactly the H2 of this dual of the logarithmic differential forms with poles on the exceptional device. So I want to compute that. Of course, by Serre duality, this is just this. So I would like to have that the sections of this sheaf is 0. So how to do that? Well, you go to so in the case of an elliptic fibration, you go to S, which is the first part here. This is my S. And the first thing that I do is to show that these sections in this S, for these 2 fibers, F1 and F2, which are the I1 fibers, is 0. And that is not difficult to do. That is something simple. Okay, so you start with this, and now we have these 2 principles. So if you add a -1 curve to the configuration, so think about this in this way. You have these 2 fibers, and you want to add some rational curves and try to do blow-ups to construct these Wahl chains. But I want to keep this obstruction 0. So how to do that? You know, if you just add some rational curves that have some other self-intersection, no -1, then maybe the obstruction is not going to be 0 anymore. But if you throw this -1 curve so that the new configuration is normal simple crossings, or if you have a -1 curve and you have a simple normal crossing and you want to erase it, so if you add or erase, then the H2 will stay the same. So if it was 0, it will be 0. And so that is the adding, erasing principle. And then you have also, you can do more or less, so you can do something similar with ADE configurations. What is an ADE configuration? So you have an ADE singularity and you minimally resolve. So there are chains of -2 curves, or this D-type or E-type. But say that these ADE configurations are disjoint from the original configuration. So you have an original configuration where the obstruction is 0, and now I put some ADE configurations that are disjoint, then it stays 0. But do not intersect the configuration, because it might change. Okay, so if we apply that, then you see that this is very simple to prove that this is 0, because here is 0. Now I blow up. So maybe you want to consider this -1 or that -1, but I do not. So stay 0. Now in here, I blow up again. So now maybe I consider that one, stay 0, I blow up. I need to consider that one, but I erase. And so I have 4, 5, 2, giving me obstruction 0, and this 4, 4 giving me obstruction 0. And you can keep going this way and construct your surface with an arbitrary Wahl singularity. So in the case of elliptic fibrations like this, it's very simple when you only use fibers. And so you can check that they are 0, and now you have no obstruction, so you can consider Q-Gorenstein smoothing and prove that the general fiber in the first case for W1 is an Enrique surface, and in the second case is a Dolgachev 2-3 surface. So a Dolgachev 2-3 surface is a simply connected elliptic surface of codiagonal dimension 1 that has 2 multiple fibers of multiplicity 2 and 3. Exactly 2, 2, and 3.
And do you know the dimensions of the deformation space for each case?
So in this case, you can compute dimensional, actually, the deformation space for each of these cases. But I don't, it's like 10, something like that. It's something that one can compute.
Right, but that shows up as a dimension of
yeah. And if you do, for example, here you have Enriquez because I constructed this quarter 1-1 and quarter 1-1. Maybe you do phi 2, phi 2, and now these two have index 3 and 3. And so you will get in the general fiber something with fundamental group set 3. And you can keep going doing that, like repeating the Wahl singularities. And you have construction of elliptic surfaces with fundamental group set over n. Now in these 5 minutes, I will show so that you have a construction of something of general type. So here I'm using the same principle, but in a different way. Now you start with a cubic pencil again, but now I want to have this I4 fiber, I1, I1. And that is something that one can do. And say that only I1s. So I4, and then how many I1s? 8. Yeah, so I have this elliptic fibration. This is my S. So now here I have these 2 fibers that I will use in the Wahl chains. So you compute with these 2 fibers obstruction, and it's 0. Now I will also use this curve, which is -2, -2, and -2. And that is an ADE configuration, disjoint from these 2 fibers. So it is 0 if I add that. And then I have the sections that are -1 curves and transversal to the configuration. So I can add that, and it's 0. So my starting point are these 3. Forget about this one. I cannot add that one because then it's not ADE. So these 3, this, and that. And now by applying this thing about blow-ups, so you blow up 8 times in this way, and you get these 3 chains. So here you have -4. There you have 3, 2, 6, 2, which is Wahl, and also 3, 2, 6, 2 in the other side. This is symmetric. You see? You know, I did 2 blow-ups here, 1 blow-up here, 1 blow-up here, 1 here, and 1 here. Now, there is no recipe for this. It's just, you see that this works. I mean, you try, and you find examples. And then we have that. You contract. You have these 3 singularities, and you have this W. But moreover, you know that the obstruction is 0. So you can consider smoothings and Q-Gorenstein smoothings of that. If you consider other smoothings, then you have other surfaces. But typically, if you achieve that this has canonical class positive, then the other ones are not, typically. And if this canonical class is positive, and you consider a Q-Gorenstein smoothing, then the canonical class for the general fiber is going to be positive. So we are in the case of a surface of general type if the K square is bigger than 0. And in this case, it's exactly 1. So by the way, How to compute the self-intersection of canonical class is very simple. You compute the self-intersection of canonical class here. So there is 0, because this is an elliptic fibration. Now we did 8 blow-ups, so here is -8. So self-intersection of canonical class is -8. And then to know the self-intersection of canonical class of W, you need to add the length of all the wall chains that you have. And I think that I have 4, 4, and 1, 9, -8, 1. So k squared is 1. And k squared is going to be 1 on the general fiber. So at the end, I have a general type surface with k squared equals to 1. Pg and Q stay constant, so they are going to be 0. So this is a Godot surface. And moreover, using topology, you can prove that it's simply connected. So the general fiber in this case is going to be a Godot simply connected surface. And that is the way you construct something like this. And when you take a general elliptic fibration with this I4 and 8 I1, then you can prove, moreover, that the canonical class is ample. And so we are in this, and so this surface that we just constructed is in this Collard-Sheffer-Barron Alexid compactification of the moduli space of Godot surfaces that are simply connected.
Sorry, I got confused. You contract a section, right?
Yeah, the section now is a -2 curve, and yeah, it's part of the contraction. You have 3, 2, 6, no, 6, 2. Yeah, this is contracted here, here, and the -4. Yeah.
And what you said is that kilo surface is in the
Yes, yeah, that is what I said. Yes, you might consider, for example, all the other singular fibers in this elliptic fibration, and those are going to be like AD singularities. So the generic one doesn't have any. You have these 3. Yeah, so I'm finishing. So there are examples for k squared equals 1 up to 4 with no obstructions. This is an example for k squared equals to 5, which is harder to construct. If you want details, maybe I can tell you later because I don't have time. But again, you start with an elliptic fibration, I4, and here there is an I4. There is another curve that I'm not using, I2, I2, and this double section and some sections. You start with that, and you obtain this. How to obtain this? There is no recipe. You use computers. So we have computer searches for this thing. And why? Because there is this big open problem, so big challenge. What happens is each time that you construct something like this from a rational surface, it turns out that maybe you don't have a smoothing, but you have a rational blowdown, which is like a fake complex surface. It's symplectic. And this rational blowdown, if you can prove that the K of W is big enough, then it's going to be an exotic blow-up of CP2 at few points. And so in this case, you have 4 points. It's always 9 minus the K squared. So in this case, it would be 4 points. This is the first example with a rational blowdown that happens. We don't know if there are complex smoothings of this surface. And then the big challenge is to do it for 6, 7, and the super challenge is for 8, because for 8, there is not even one example. For 6 and 7, not using rational blowdown, you can find some examples that are very few, but for 8, there is no example. And there is no obstruction to find example so far. But there is one obstruction that you need to find only one chain, and should be very long wall chain that you contract, and then the K squared is 8, and KW is big enough.
So just to be clear, so the challenge is to start off with a rational surface.
Yes.
And blow it down and then smooth it out.
And blow up to form these wall chains, and now contract, and you want to have the, no smoothing, you want to have that the canonical class is big enough, so positivity, and the K squared has to be 8.
But you don't care if you can smooth it out or not.
No, I don't care. Yeah, the K squared phi, we don't know if we can smooth it or not. So that is the challenge. You can do this with K3 surfaces. You can start with, there are plenty. There are even more situations to consider for K3s, and you can do the same game. You can find K squared between 1 and 9, and up to 12. So 10, 11, 12 have obstruction. So, and then we don't know what happens after 13. We don't have example. And the computer cannot find anything. I'm finishing. with Javier Reyes, we have this computer search, and when you fix k² between 1 and 4, for example, you can find, so let me show you this. For k² equals to 3, you can find 2,104 different Wahl singularities in these degenerations. So in this moduli space, you can find that many different singularities. So it's very crazy, this boundary. And for k² equals to 4, there used to be just 2 examples. And now this computer can find examples. Now there is 1,246 different examples with different Wahl singularities. And many of them, no, all of them in here are smoothable. And
Are they specializations of one another?
yes, so sometimes you can see something like that. Yeah, it would be very nice to connect these. Right. Yes. Yeah, and in this case, in the first case, you have a modular space expected dimension 8, then 6, 4, and this is a surface. This is 2. So what you see in the boundary are curves. And you have that many Wahl singularities, which is crazy, very crazy. And this is the kind of list that the computer produces. For example, one line is one example. And here it is giving you like 2 Wahl singularities. There you have the N and the A, the N and the A. And then it's checking that the canonical class, if it's Neff, Q effective, obstruction, and all those. And if you want to look at the example, you put this number, and there is another program that gives you the picture, how to do it. But we don't have a systematic recipe. Okay, I'm over.
Let's take